Superheating gold, breaking the entropy catastrophe limit with extreme physics. Imagine defying nature's limits. Researchers have pushed gold to an extreme by superheating it to over 14 times its melting temperature, momentarily sidestepping what is known as the entropy catastrophe. In a breakthrough experiment, a thin film of solid gold, just 50 nanometers thick, roughly half the size of many viruses, was heated with a powerful X-ray laser in a span of only 45 femtoseconds. That is, 45 millionths of a billionth of a second. This rapid energy delivery raised the temperature so dramatically that every atom in the sample began to vibrate intensely, essentially increasing its kinetic energy, which is directly related to temperature. The entropy concept, a fundamental idea in physics, represents the level of disorder in a system and is governed by the second law of thermodynamics, which states that in an isolated system, entropy is bound to increase. To put it simply, water in its liquid form is more disordered, or has higher entropy, than its structured solid form, ice. Normally, solids are less disordered than liquids, but nature allows for extreme exceptions. For instance, liquids can be supercooled below their freezing point, reducing their entropy to that of a solid. Conversely, if you heat a solid well beyond its melting point, it can reach an entropy level similar to that of a liquid, a phenomenon referred to as the entropy catastrophe. For gold, which melts at 1064 degrees Celsius, or 1947 degrees Fahrenheit, this important critical temperature is roughly 3 times its melting temperature. But here's where it gets controversial. In practice, reaching such extreme temperatures in a solid material is fraught with challenges. In the natural border, various physical processes, sometimes described as a hierarchy of catastrophes, tend to prevent a solid from maintaining its structure once it approaches these conditions. The rapid laser-driven heating approach used by Thomas White and his team at the University of Nevada, Reno, is a clever method to beat these challenges. The technique involves energizing the electrons, which are loosely bound to the positive ion lattice in metals like gold, so that the energy is quickly distributed throughout the material. This fast energy transfer causes the atoms to vibrate violently without giving the sample enough time to expand, thereby maintaining its crystalline structure temporarily despite the extreme conditions. It is important to note a critical nuance in these experiments. Temperature is typically defined as the average kinetic energy of particles in systems at equilibrium. In these ultra-short laser heating experiments, the system is kicked out of equilibrium, meaning that the standard definition of temperature might not fully capture what is happening during those few fleeting moments. This aspect invites debate among experts about how exactly to interpret the results. And this is the part most people miss. While these findings open up exciting new possibilities for understanding phase transitions in materials, they also challenge our conventional wisdom about temperature and disorder. The implications of this study are significant. By mastering the process of superheating and controlling the transition between solid and liquid states at such extreme conditions, scientists might unlock new methods for material production and gain a deeper understanding of phase transition at a fundamental level. So what do you think? Could these results revolutionize material science, or are there hidden pitfalls in our current understanding of thermodynamics? Share your thoughts and join the discussion. For further details on this breakthrough, the study is published in the journal Nature. Superheated gold breaks physics limits. New method challenges entropy theory. Imagine gold defying the laws of physics. A groundbreaking study has shattered decades-old theories, redefining our grasp of superheating. Measuring the temperature at extremely hot materials has always been a formidable challenge. Whether it's the fiery plasma of the sun, the intense core of planets, or the extreme conditions within fusion reactors, these warm, dense matter states can soar to hundreds of thousands of degrees Kelvin. Accurate temperature readings are vital for understanding these complex systems, yet they've remained elusive until now. We've mastered density and pressure measurements, but temperature has been a persistent enigma, admits Bob Nagler, a scientist at SLAC National Accelerator Laboratory. This mystery has hindered our theoretical models for years. In a landmark breakthrough, researchers have, for the first time, directly measured the temperature of atoms in warm, dense matter, as reported in Nature. Unlike previous methods reliant on intricate models, this novel approach directly tracks atomic speeds, revolutionizing our understanding of the material world. A team led by Nagler and Tom White of the University of Nevada, Reno, includes experts from renowned institutions worldwide. Their decade-long effort has bypassed the usual measurement hurdles, such as the fleeting nature of extreme conditions in labs and calibration difficulties. We've achieved a direct, unambiguous measurement, setting the new standard for the field, White asserts. Under extreme conditions, materials can transform into exotic phases with unique properties. At SLAC's MEC instrument, the team used a laser to superheat gold, causing its atoms to vibrate at speeds reflecting their temperature. Ultra-bright X-rays from the LCLS then revealed these speeds, and thus the temperature. This technique showcases LCLS's cutting-edge role in laser-heated matter research, says Siegfried Klenzer, a co-author. The real shocker? The gold reached 19,000 Kelvin, far beyond its melting point and the entropy catastrophe limit, while remaining solid. We didn't break thermodynamic laws, we showed that rapid heating can prevent these catastrophes, White explains. This discovery suggests that superheated materials might have no upper limit if heated quickly enough. The implications extend to fusion energy research, where understanding material behavior under extreme conditions is crucial. Nagler believes researchers have unknowingly surpassed the entropy catastrophe limit before, lacking a reliable measurement method. This technique opens doors to countless new discoveries, he infuses. Already, it's being used to study materials replicating planetary core conditions. The potential for advancing fusion energy and understanding extreme matter is immense. Gold defies physics, superheated to 14x melting point without melting. Imagine the metal so resilient it can withstand temperatures 14 times hotter than its melting point without even melting. Sounds like science fiction. Yet, this is precisely what researchers have just observed with gold, challenging long-held theories about the limits of superheating. But here's where it gets controversial. Could this mean that solids have no upper melting point at all, and that thermodynamics as we know it might need a complete rewrite? Let's dive into the details. Superheating isn't new. It's the phenomenon where a substance heats beyond its melting or boiling point without changing state. Picture a cup of water in a microwave. If the container is perfectly smooth and undisturbed, the water can exceed 100 degrees Celsius without boiling. But the moment you stir it, it erupts into steam. For solids, physicists have traditionally believed there's a hard limit to superheating, called the entropy catastrophe. This theoretical threshold, roughly 3 times a material's melting point, is where the entropy, a measure of disorder, of a solid would theoretically surpass that of its liquid form. Beyond this point, the second law of thermodynamics, which states that entropy can't decrease in isolated systems, would be violated. But now, a team led by Thomas White at the University of Nevada, Reno, has shattered this assumption. Using a laser pulse lasting just 45 quadrillionths of a second, White's team targeted a 50 nanometer thin gold sheet. By analyzing how reflected X-rays shifted in frequency, essentially tracking the energy gained by the gold, the team measured temperatures reaching 14 times gold's melting point. We looked at the numbers and thought, can this really be accurate? White recalls. After verifying their data, they realized the answer lay in speed. The ultra-fast heating left no time for entropy to accumulate in the solid state, allowing it to surpass the entropy catastrophe point without breaking thermodynamic laws. We haven't violated the second law, White clarifies. The rules still hold, it's just that we're playing the game faster than the system can react. This discovery raises a tantalizing question. If gold can defy expectations, what about other materials? Sam Vinko of the University of Oxford suggests this technique could revolutionize how we study extreme conditions, like those in planetary cores. We lack tools to measure solid temperatures on femtosecond timescales, he notes. This could change everything. Yet, the biggest mystery remains. Is there any upper limit to superheating? Or have we only scratched the surface of thermodynamic flexibility? And this is the part most people miss. The implications go beyond gold. Could this mean that with enough speed and precision, we might outpace thermodynamics itself. Some argue this hints at a deeper truth about how matter behaves under extreme conditions. Others see it as a reminder that even well-established laws have hidden loopholes. So what's your take? Can speed truly outmaneuver the laws of physics? Or is this just a temporary loophole in our understanding? Share your thoughts, because the debate is only just beginning.